Hi, good evening, everyone. Welcome to the week 5 live coding session. Before starting the session, one question: is there any topic remaining from the open session? Is anything pending?
Yes, sir. We discussed first three searches like the extra.
Okay, Bellman and Flood Varsal.
Yes, sir.
Okay, so that spelling part is not discussed.
No, sir.
Okay, okay. Yeah, so I have already released the problems on the Replit. Those who have cleared this part, spanning tree, Kruskal algorithm, and Prim's algorithm, they can start to solve the problems, and we will just revisit this topic, spanning tree and Prim's algorithm. Then we will go through this live coding problems.
Sir, you will discuss the spanning tree. I just joined.
Yeah, so I think it is pending. This topic is pending, not covered in the previous session. Okay, so I'll discuss these things, and also I have released the problems. Three problems I have released for the week 5. So if this part is clear to everyone, so you can start to solve the problem. Any specific query from week 5 before starting the session? Okay, so some have already started. Yeah, so I have released three problems in the week 5, and these problems are based on the week 5 content, that's shortest path algorithm and spanning tree algorithms. Okay, so if both all the concepts are clear of week 5, you can start solving from the week 5 problem number 1.
Week 4, we don't have any problem, is it?
No, week 4 we have already done in the last week.
Oh, week 4 is there. Huh?
Okay, in the last live coding session.
Okay.
Okay, today is the week 5 live coding session.
Okay.
And week 4 we have also released the solution on the Replit. You can see.
Oh, all right. Okay.
Okay. Okay, now I'll start with the spanning tree part. Okay, so this is the topic. I think it is remaining completely. Uh, so first thing is spanning tree. What is spanning tree? Can anyone tell me what is spanning tree?
All all uh, all vertices are connected and there is no cycle.
Okay, yeah, correct. Okay, so first we will discuss the spanning tree terms. So spanning tree means this is a tree, okay, and this tree is actually we creating using a from the graph. So we have one graph and we are converting that graph into a tree. Okay, so tree definition is that tree is so all the vertices are connected with the minimum number of nodes and there is no cycle. Okay, so we will convert our graph into this form, tree form. So our all nodes which are present in our original graph, should also remain connected in our tree. Okay, so because of that we are giving this term here tree. Okay, so some points are also given, adding an edge. So if in the tree, if we connect any edge between two vertices, so definitely it will create a cycle. Okay, and suppose if we have n vertices, so how many number of edge are possible in
N
this?
minus 1.
Yes, correct. Okay, so all the, if all the vertices are connected in the tree, so definitely we need n minus 1 edges to connect all the vertices. Okay, if we have n vertices. So this is the things in the spanning tree. So here we have one graph, and we need to convert that graph into a spanning tree. So there are multiple possibility. We can create many number of spanning tree for the one graph. Okay, suppose I'm taking one example. So like this, we have one graph. I'm taking simple graph. Okay, like this. Okay, so this is a graph.
Sir,
Now,
how many spanning tree possible? How to no? Mean there could be many spanning tree, no?
yes, yes. So that depends on the graph, how the edges, how many edges are there. Okay.
Means is there any algorithm or such question may be asked?
Uh, how many spanning tree are possible? Yeah, mm, that yeah, we can create this type of problem also, but I think there is no straightforward formula is available. Okay. So for a small graph, we can identify that manually. But if suppose if we have a large number of vertices and many vertices are connected to each other, so we cannot directly identify based on the number of vertices and number of edges, so how many spanning tree are possible. Okay, so we need more information in that case if we want to find out this information. Okay, so regarding the spanning tree, so I'm just simply marking that if we convert this graph into a spanning tree. Okay, like I can create many spanning. Okay, suppose weights are also given. Okay, so 10, 5, 3, 4. Okay, so B this, if I'm connecting in that way, I'm removing one edge, B to D. Okay, now this is one possible spanning tree. You can see now all vertices are connected, and these this is a tree. Okay, so now weights are remaining weights are 5, 3. Okay, another possibility is that if I remove edge A to B, then we will get this type of tree like this. Okay, this is also a spanning tree. So if we mark the weight of the edge, so 5, 3, 4. Similarly, we can also create another type like this. Okay, so 10, 4, and 3. Okay, so there are multiple possibility available. So now if we add the weights of all edge in spanning tree, okay, so we are getting different sum of the weights. Okay, so here we are getting 10 plus 5 plus 3, so 18. Okay, total value we are getting 18. If we calculate the sum of all edge weights for the second spanning tree, we are getting 5 plus 4 9 plus 3 12. Okay, and for the third one we are getting 10 plus 4 plus 3. Okay, this is 17. So for the each spanning tree, we are getting different types of total sum of the edge weights. Okay. Now our goal is here that we want to find out the spanning tree which contains the minimum possible sum of the total all the edge weights. Okay. So actually that spanning tree is called the minimum spanning tree. minimum cost spanning tree. Sometimes we call minimum spanning tree MST, or sometimes we also call minimum cost spanning tree, minimum weight spanning tree. Okay, so these are the different terms we use generally for the same thing.
So we can think of these as, let's say, a city wants to build metro stations, so you want to spend least amount of money to connect all the stations, something like that.
Yes, yes.
Yeah.
Yes, similar type of problems. One problems are given, I think, in the assignments. Suppose we want to connect all the city with the fiber coaxial cable or like fiber cable. Okay, and but we want to use the minimum length of the cable.
So
Okay.
is it the minimum number of edges required to cover all the vertices is the minimum?
Yes, so that minimum number of edges actually is that this spanning tree is where the each vertex are connected.
Yeah, but now the minimum cost means the minimum weight among the.
Yeah, minimum sum, okay, total weights, that should be minimum. Total weights of the edge. If we add all the edge weights, so that value should be minimum.
There should not be any redundancy in joining, is it?
No. Redundancy means
Repeatedly.
no, we are not getting any repeating things here. Yeah, repetition are possible in the total weights.
That
So
should not be there in that one, no? In the minimum
yeah,
cost factor.
no, so that are possible.
Possible?
Yes. So this is possible that we can also find out two different minimum spanning tree which contains the same minimum cost.
Same cost, is it?
Yes, yes, this is possible.
Oh, okay.
Okay.
So
So
it's not the minimum spanning tree is not unique.
yes, this is it is not unique.
Okay.
Okay. If all the edge weights are distinct, okay, if all the edge weights are distinct, then we can say that our minimum spanning tree will be unique.
Okay.
Okay, if the values of the edge weights are repeating or duplicates, in that case our we can get more than one spanning tree.
Okay, sir.
Okay, so this is the main thing. Our goal is here to find out this minimum cost spanning tree. Okay, so these are some points we need to know. A tree on n vertices has exactly n minus one edge. Adding n edge, a tree must create a cycle. So these are simply a tree property, and these property are also applied on this spanning tree because this is also a tree. So this is the problem. Now, how we can find this information from the graph? So there are two standard algorithm we used. First is Prim's algorithm and second is Kruskal algorithms. Okay. So the purpose of the both algorithms are same. Both will return the minimum spanning tree cost and minimum spanning tree, but the logic is different. Approach is different. Okay, so first we will discuss the Prim's algorithm. So how Prim's algorithm works, and then after that we will discuss the Kruskal algorithm approach. Okay, I'm taking one graph. Okay, so suppose we have this graph. Okay, and we want to find out the minimum spanning tree using Prim's algorithm. So how actually Prim's algorithm works? So first thing we will understand by the logical approach on the graph how the Prim's algorithm works, and after that we will look the implementation. So you will easily relate the implementation with the working. Okay, first thing we can start this Prim's algorithm from any vertex. Okay, so we can start from any vertex. We can select 0, then we can start from 1. We can select any vertex to start. Okay, after that we will start the process. Suppose I am starting 0. Okay, so I am starting 0, and we will also maintain this information in our data structure, like that which node is visited, which node is marked, like this information we will store. So we are starting from 0, and we are marking that this node is visited. Okay, this is the first node, this node is visited. Now we will check that how many edge are connected from this. Okay, so from 0 we are getting 0 to 1 and 0 to 3. Okay, and 0 to 1 contains 10 weight, and 0 to 3 contains 18. Okay, so this is the first process. We will start from the node, and then we will check all the adjacent, and we will check the weights of the edge. And this is the after that we will assign the weights initially. Okay, so initially we will assign the weights or 0 on the source node where we are starting. From the remaining we assign infinite, like this. Okay, so this is the initial process. After that, when we this is similar to Dijkstra algorithm, a little bit similar to Dijkstra algorithm. If you know Dijkstra algorithm, this will also is similar, only little bit difference. So so we will check this 10 and 18. Now you can see if we are taking 10, the previous distance is infinite. Okay, so if we are getting less distance, so we will update. Okay, for this edge, so we will now update is this. So this will become 10, and next will become 18. Okay, so 18. Okay, after that we will select so now this node is visited. Now remaining vertices are not visited. So from the remaining nodes we will select the vertices which have minimum distance. Okay, so you can see the vertices 1 have minimum distance 10. Okay, 3 have 18, 2 is infinite, 4 is infinite. The smallest one is 1. So we will select this next visited vertex. At the time of selection, we are simply marking this value. So this value actually we are getting from this edge. Okay, so that means this edge is considering, okay, in a MST. So we are simply considering this edge into our MST. So this is the first edge, 0 to 1. Okay, after that we are selecting this one vertices. Now we will mark this as a visited. Okay, and from this visited vertex we will once again check what are the adjacent vertices of this from this one vertices. Okay, now you can see you can move 1 to 2. Okay, 1 to 6. Now this time in the MST we will update the previous distance by the current edge distance, not the path. Okay, in the Dijkstra algorithm we will always update the distance by the path value from the source, total distance. But here if I'm coming on the 2 from 1, then we will update, we will check the distance 20 only. Okay, so 20 20 is smaller than infinite or not. Okay, I'm not adding the previous distance, because this time we are simply finding out the smallest weight edge. So I'm simply comparing 20 is smaller than infinite. Yes, correct. So I'll update this 20. Okay, and I'm simply update the vertices which is not visited. Okay, so now 1 to 3. 3 is also not visited right now. So I'm getting 6. Okay, I'm getting 6, and previous is 18. Okay, which this is smaller, 6. Now we will choose the same things. We will find out the next smallest weight vertices. Now next one is 3.
Sir,
Hmm?
actually 6 or 16?
This is 6.
No, 3.
Yeah, so that things I've said that this is not a Dijkstra algorithm. In Dijkstra algorithm we added the previous distance from the source, but
Right.
here we are simply comparing this current edge from this 1 to 3.
Oh, okay.
Okay, here actually we are focusing on the edge weight because we want to uh, find out the smallest weight edge that should come in the MST.
Okay.
Okay, so because of that we are simply comparing the 6 by the 18. Okay, so now 6 is smaller than 18, then we will update this. Okay, now this is the next updation. Now we will select the next vertex is 3 because now this contains the smallest weight in the remaining. Okay, so 6, 20 and infinite, this contains the smallest. Now from 3 we can move to the 0, but 0 is already visited, so we will not check this. Okay, so from 3 to 1, but 1 is already visited, we will not check this. So now you can see when we are selecting 3, so we are getting this 6 weights from the 1. So that means this we are considering this edge. Okay, and now second this one, and after that from 3 we will update the weights. So 3 to 4. Okay, so 4 is not visited. Now the current edge weight is 70, but the previous is infinite, so 70 is smaller than infinite, we will update this. Okay, now this step is complete. Okay, and we find out that 2 edge, 0 to 1 and 1 to 3. Now same step we will repeat again. So now this time we are finding the 20, this is the smallest one because we have only two remaining, 2 and 4. So this is the smallest one, 20. Now we will select this vertices. Okay, and 20, this value, where from we are getting this 20 value? From 1. Okay, so 0 to 1 we have selected, and 1 to 3 we have selected, and now 20. Okay, so this 1 to 2, this edge we have selected. Okay, so now this is also considered as a spanning tree edge. Now 20. Okay, so from 20 from 2 vertices, if we check, the adjacent vertices are remaining which are not visited is 4. Now the current edge weight is 8, which is smaller than 70. Okay, now this is 8. Okay, now all things are completed. Now all vertices are visited. Now all the remaining vertices is 4, which is not visited, so we will select next one is 4, and this 8 weights we are getting from 2, so this 2 to 4 edge will be considered in a spanning tree. Okay, and now there's no adjacent remaining which is not visited. Okay, so the our process is complete, and finally we are getting these edge in our spanning tree.
So,
Okay.
but like we came on 4, then
Hmm.
we had updated 4 to 8 when we were at 2, right?
Hmm.
So what do we do when, like, how do we decide that we are adding this edge 2 to 4 to the spanning tree?
Yeah, this type of information we have to maintain if we are updating the weights. Okay, so where from we are updating, what are the parent nodes, so
Hmm.
this information we can maintain. Okay, so we can do the same things in the different way. In the implementation time we can use another data structure, or we can do the same things by the different implementation, but the logic is this is the logic actually of the Prim's algorithm. Okay, so how we are finding out the
Sir, here all weights are different.
sorry,
Sir, here all weights.
Ritik, your
Sir,
voice
here
is
all
not
these
clear.
weights are unique.
Sorry, Ritik, your voice is not clear, can you repeat? Hello.
Sir, I am saying, is my audio now clear?
Now it is clear.
Sir, I am saying, sir, here all edge weights are unique.
Mm-hmm.
So we will find unique path, means there is only one spanning tree possible, right?
Yes.
So there could not be other spanning tree.
Yes.
Okay.
If the edge weights are remain duplicates, still our implementation will select only one. Okay. because it is processing by either by it will read the element by the value one by one. So if we are getting two weights, similar weights on two vertices like 2 and 3. Okay, so these are the vertices. If we are finding 5 edge weights on the 2 and 5 on the 3, so still when we are finding the smallest weight edge weight vertex, okay, so we will process our vertices in any particular sequence from 0 1 2 3, like, okay. So if we are finding the smallest value at 2, so we will select this one first. Okay, but logically more than one spanning tree are possible if one value are duplicates. Okay, but our implement will return maybe only one spanning tree.
But here, if it is not repeating, we will get only one, and there is only one possibility.
Yes, then only one possibility is there. Okay, so this is our final spanning tree: 0 and 1 and 3 and 2 and 4. Okay, now what is value are 10 and this is 20, this is 6 and this is 8. If we add all the weights, then we are getting 30 36 and 44 total weights of this spanning tree, and this is the minimum. Okay.
Okay, sir. So you will probably be maintaining a count of the total weight.
Yes. So some information you have to maintain, and any logic you can use to perform the same logic. So implementation, now we will see the implementation, how these things we are doing by the implementation. Prim's algorithm. Okay. So this algorithm is here. Our data structure we used is W list. Okay, adjacency list. Now first value we are finding out the infinite. Okay, so in Python you can also simply assign the infinite value by the float by converting the some there, I think there is one way where we can simply assign the finite value in the negative or positive. Otherwise here what we are doing, we are simply finding out the maximum weights, and we are okay, so maximum weights okay, maximum weights, and we are what we are
Just
doing.
adding one basically.
It is taking we are just identifying what is the maximum weight, and then we are multiplying it.
Okay. So actually here we are not adding the previous weights. Okay, so because of that we are selecting the maximum and adding only one. Otherwise in the Dijkstra case we are also multiplying the maximum weight by the total number of edge. Then we are adding the one. But in this case,
Yes,
okay, so at the time of updation of the weights, we are not adding the previous path weights, so that value will not go over this value. Okay, so because of that we are deciding this as value as an infinite value. After that we are maintaining this visited, distance and tree edge, all three value for our program. Okay, so visited is a dictionary, distance is a dictionary, and tree edge is a list. Now this is the initialization. We are initializing all vertices as visited value is a false and distance value is a infinite. Okay, after that we are starting from vertex 0. Okay, so if we are starting from 0, so we are assigning this visited 0 equal to true, and also we are assigning this distance. So for VD in W list 0, what we are doing, distance of V, this 0, what distance we are assigning to the
initializing the distance, right?
All neighbor of 0, we are assigning distance to them.
Okay, I got it. Yeah, correct. So now we have started the process. Okay, so we have started the process here, Now all the adjacent vertices of 0, okay, and we are assigning the distance from our 0 vertex, okay. So this distance we are assigning for the each adjacent d. Now we are repeating this process for I in range 1 to length of the total, that means total number of vertices minus 1. So we are starting from 1, and this will go, okay, so total number of vertices minus 1, okay, this loop is running. After that we are finding min distance, okay, so min distance we are simply assigning equal to infinite, and after that we will compare this, and next v node equal to none. So this is the initialization part, and we are checking these things in our program, okay, for u in wlist key. So that means we are traversing all the vertices. Now for v comma d in wlist u. So for each vertices of the graph, okay, we are traversing, and now we are finding out the all adjacent, okay, for each vertices. And if our all adjacent are visited, okay, so if visited of u equal to true, not, okay, so why we are to what condition?
Sir, here we are traveling, I think, from only the
From U to
vertices
V.
that are visited. Means we are not checking whole thing. We are only checking just the nearest one, just the new added vertex.
Hmm.
Okay, some, I think some logic is different here.
So like we are going from U to
Sir,
V,
actually
right?
there are two implementation. In one implementation, we check all the distance. Mean infinity we also check. And here we only check for the vertices that we have visited. Means after zero, we will only check the neighbor of zero only.
Not visited. Okay, okay, okay. So visited. Oh, okay. So this is the U. We are checking. Oh, okay, okay, got it. So yes. So we are selecting from visited vertex. Okay. So those vertex have visited to unvisited vertex. Okay. So this is U, and this V is representing a unvisited vertex. Okay. So this should be visited, and this should be unvisited. So in this case, we are checking only for those. Okay, so if the source vertex is visited and the destination vertex are not visited, and current distance, okay, so this is representing a distance is less than or equal to min dist, which we have finalized from here. That means simply what we are doing, we are finding out the minimum distance. If we check the previous graph, some working is little bit different for this. So what we are doing actually 0, this is infinite, 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 okay. So now in the first step, okay, so this vertex is visited, we mark this vertex is visited. Now we are completely traversing the graph every time, and we will check that the vertex, source vertex, which is visited, okay. And now, so from this visited vertex, how many adjacents are not visited, okay. So initially in the first step you can see how many adjacent are not visited. So this is
Only
marked
one and three.
1 and 3, okay. So for 0 we find out that 1 and 3 are not visited, okay. So in that case, so this process, so this is the first thing, and we will check these things for the whole graph. So we are running the complete loop, okay. So we are getting two value here, so okay, so 10 and 18. After that we will check for 1, okay. So 1, but this is not visited right now, okay, so we will skip this process. Now we will check for 2, this is not visited, okay, so we will skip this. Now we will check for 3, this is not visited. Now we will check for 4, not visited. So in the first iteration we are only finding out these two value, okay, 10 and 18. So in this complete process, so we are starting min dist equal to infinite, and we are comparing the current distance, okay. So we are comparing the current distance infinite we are getting 10. Now we are comparing this 10 is smaller than infinite. Yes, so we are assigning min distance equal to 10. Then now the remaining distance is 18. Okay, so 18 is less than 10. No. Okay, so this information we are storing in the this iteration. Okay, so we are assigning this min dist equal to infinite, and after that we are completing, we are checking for the whole graph, and we are only checking the visited vertex to unvisited vertex edge. How many edge are available which are coming from visited vertex to unvisited vertex, and all the from all the edge we are finding out the smallest edge weights. Okay, so these things we are checking by this condition, and at any time this condition is true, we are simply assign min dist equal to d, next v equal to v, and next e equal to. Okay, so we are storing this edge information also. Okay, so this is the complete one cycle. After the second cycle, okay, so in the first case we will find out this one edge information. So you can see in the code, so u comma v. Okay, so in the first case we are checking from 0, and what we will find out, so v which contains the smallest distance, so we will find out the uh, this 1. Okay, so 0 comma 1 we are storing in our result. And what is the weights, we will also store this weight in our result in the code.
So,
Okay,
but
so
wouldn't we lose this information in the second iteration of this?
no,
Because
same
we're not
same.
using it anywhere, right? That like minimum distance next v next t. Not storing it anywhere.
No, I think this part is also remaining na, in this
So this
graph.
is outside the loop, right?
No, no, loop is running from here. This is inside this first loop.
So this
14.
minimum distance d next v equals v next t
Hmm.
equals to uv, right?
Yes.
The moment we go to the, because we are going from for u in wls.keys,
Huh.
right? And then
So,
yeah, so we
yeah,
are going through the adjacent vertex of u, right?
yes.
And then we are assigning all those things. But then when we go to the next
Okay.
u in the wls.keys,
Uh-huh.
at that moment we are going to lose this information because that new
No, so
thing.
no need to maintain this information. We are assigning all this information in our result data structure. Okay, so visited we are marking. Okay, so this next we are marking here. Okay, and after that we are also maintaining this tree edge append next t. We are storing the current edge which we have selected. So this uv edge, okay, next e is contain the edge which we
So
find out the
the
smallest.
so the last edge which we are going to be visiting, we are going to store from the end, right?
Hmm? Sorry, last edge.
Because we are for u in wlist.keys. So the last u, whatever the last key value is there in
Hmm,
that list,
hmm.
that for that only we'll have those values
No,
of.
no, no. So this condition is not true. No, for this, when we are traversing complete graph, so this condition should be satisfied
Okay, okay,
when we
okay,
are entering inside this.
okay. Sorry, I didn't see
Okay,
that.
so this
Oh,
visited u, yeah, that means source. We are simply finding out the all edge where the source should be visited and destination should be not visited.
hmm.
Okay, only we are checking for those edges, and we are finding from all these type of edge we are finding out the edge which contains the minimum distance. Okay, so this is the first part. First we are storing this information, also the same intent we are also maintaining these things. So for tree edge,
Sir, why we use distance of v? What is use of distance of v here?
distance of v, this one you are talking about.
Yes, sir. What is use of this?
Okay, let me check. Yeah. Okay, for VD in W next V, if not visited V, if D is less than distance V, we are marking distance of equal to D. Okay.
So you're comparing if you're going to update that if the cost is
Yeah. Okay.
lower.
So yeah, here you can see now this distance. Okay, mean distance. We are okay for infinite.
So
And D.
after you calculate the UV, then you're talking about next V, right? So when you do the next V, it is comparing the distance of next V with the V which was traversed before the preceding edge. So the distance is of the current one is less. I mean, current one is better. Then you keep the other one. I think that's what it's doing here.
Okay, but after
No,
that,
I think yeah, he is correct. We are not using this distance v anywhere in the code. Okay, distance v 1 second. Yeah, wasted v. Yes. So we are not updating this distance of v. Okay. Oh, yeah, we can use this information after distance of v equal to d. Okay, distance of v. Yeah, finally, if we want to find out the total cost, okay, at that time we can use this information. Otherwise, there is no use of this part. Okay, here what we are collecting simply tree edge. We are collecting tree edge, but if we want to find out the total cost, then we have also once again we have to traverse all the edge weights in the graph, and then we have to sum the all edge weights.
So you sum all the values in the distance dictionary.
We can find out the distance from the distance dictionary, and then we can directly get this value based on the edge. Or I am not finding any particular use. If we are returning, so in this implementation, if we are returning the edge only, okay, so then in that case there is no use for this part.
It also mentions the cost is 44, right? So that means if we add
Yeah.
up the
This is mentioned. This is not coming in the output for this implementation. Okay, here we are simply returning the total number of edge we have selected for the minimum spanning tree. So based on this information, we can also find out the total. So what weight this edge contain, what another edge contain the weights. So if we add all the weights, we will get this 44. Okay, so for this implementation, if we are simply finding out the only edge, then you can ignore this part.
So it looks like it is a modification of BFS. In BFS,
Not BFS,
no,
no,
well, I mean, we are starting from a node. We are looking at all the possible adjacencies. Like in that case, we used to add them to the queue. But here, the modification is, I'm not going to traverse through all the neighbors. I'm only going to go to the neighbor which has the minimum weight.
yes, but that your
It
neighbors.
seems
So we are not going to explore all the neighbors. I'm only going to explore the neighbor which
where
will
one
cost
side
me
is
the least.
where one side vertices is visited and another side is not
Correct.
visited.
Two conditions. Yeah.
Yes, this is we are maintaining in this case.
Yeah.
Okay, so if we repeat the next cycle, okay, so we are not using the distance for this case. So you can see if we are selecting, so we have marked this as a visited, okay, in the first cycle. Okay, this is already wasted. Now we will repeat the same process completely. Okay, we will start from the zero. We will check from the zero. Okay, so now from zero to one, we will not consider this as, because here both side vertex are visited. Okay, now 0 to 3, yes, so here 0 is visited but 3 is not visited, so we will select this edge. So 0 to 3 edge we will select. Now we will traverse from 1, so we will check for so 0 to 3 contains the 18. Okay, now 1, okay, so we will select from 1. Okay, so 1 to 0 we cannot select, 1 to 2 we can select, yes, 1 to 2 is 20, and 1 to 3 we can select, yes, 1 to 3 we can select 6, and after that we will check from the 2. Okay, so now you can see this 2 is not visited and 4 is also not visited, so we will not check for this. And similarly, from 3, if we select 3, so 3 is also not visited and 4 is also not visited. So we are finding all these 3 edges, and from these 3 edges we are finding the smallest minimum distance is 6, which is belongs to 1 to 3. Okay, so 1
Sir,
to
one
3 will.
question, sir.
Mhm.
Sir, please connect 0 and 1 by one edge and 1 and 3 by one edge.
0 and 1.
And 1
Okay,
and 3.
okay,
Please
yeah.
draw the line. Yes, sir.
Huh.
If we are not using the distance that was mentioned,
Mhm.
then why will we select 1 and 2? Why we will not select 3 and 4?
3 and 4. No, we are selecting these things based on this information. Here we are storing this. We are
The
checking all
distance,
the
the
edge. We are,
distance information.
but this distance. So this is not a distance. This is a edge. Okay, this is the edge weight. We are not checking anywhere distance.
Sir, but like we are updating the distance, right? And that distance is going to be used in the loop
No,
when
where
we,
we are using in the loop, you can see.
like for I in range this 1 to this, right? Length WLS dot keys, the overall loop,
Uh-huh. Uh-huh.
right? Then we are having for U in WLS dot keys, for VD in WLS dot WLS U, right? So
Mm-hmm.
so this D thing we are using, right? That D is less than
Yeah,
the
this D
minimum
is
distance.
not this distance.
Yes, but this distance is
Yeah,
coming from W list, right?
yeah, this is coming
And
from
then
the
then
data structure.
then we are saying for VD in W list next V, if not visited, if D is less than distance of V,
Mhm.
distance of V is D. But this D is actually the distance of V, right?
This is
मतलब,
U to V.
yeah,
U to V.
U to V, U to V.
Yes.
Yeah, so if this is the distance, if we are changing this value in W list and then we are using it in the next iteration on this condition, right?
No, we are
V is
not changing in the W list. Where we are changing in the W list?
W list is an adjacent, मतलब it's a weighted adjacency list, right?
Yes,
It's
but
a
we are not
dictionary.
changing. We are not changing that data structure.
Okay.
You can see. Can you see in the implementation where we are changing in the data structure?
Yeah, okay, we are not changing that. True. We are just taking that value from there,
Yeah,
but we are
we are
not changing.
simply reading the edge distance value. Okay, so in dictionary actually we contain like U, and this is the key, and inside the list we are simply contain the tuple type of information. Okay, so V comma D, like this. Okay,
Okay.
V1 comma D. So we are simply reading this all adjacent, so which are the adjacent of the U, all the adjacent, and we are reading the value V comma D, and we are reading this D value here. Okay.
Okay.
So in some sense, D is the cost, minimum cost you'll incur to
No, D is
over.
the edge weight here.
Yeah,
D is the edge weight from U to V.
you to be. Yeah,
Edge weight is a cost, sir.
Hmm?
Edge weight is a cost, no?
No, in this implementation, we are simply returning the edge, which we are including in our MST.
So it's like we can calculate the minimum cost spanning tree without even looking at the distance, just by like we are looking at the distance, but we are not summing everything
Okay.
up.
Okay. So for the total calculation of the distance, simply you can take one another variable like total cost. Okay.
So you are not calculating the minimum cost. Right?
Okay, yeah, I'm just writing the modification equal to 0. Okay, and after that, when you are coming here, okay, coming here in this line before this, simply write this total cost equal to or plus equal to min dist.
Yeah, that's it.
Okay, so in this case, you will get the total cost also. Why we are running this loop from 1 to total number of vertices? Because we are simply assume that in each iteration we are selecting one edge. and in our spanning tree we will get n minus 1 edge. Because of that, this loop is running n minus 1 time. Okay, in each iteration we are selecting one edge with minimum weight. So this is happening in our implementation.
Sir, can you please walk from start to end because we are going back and forth? There was a flow of thought was really broken.
You are asking for this implementation?
Yeah, that implementation, because we were quite frequently back and forth, we were going and losing the.
So I'm just quickly just giving the idea of the
Yes, quickly
implementation.
just to walk through, then it will be better.
So actually, what we are doing in this, we are performing one loop for I 1 to n minus 1. Okay,
N minus 1.
total n minus 1 time we are running this loop, and this loop is basically we are running for the n minus 1 edge. Every time what we are doing, we are simply traversing the whole graph. Okay, and we are traversing all the edge, and we are finding out the minimum weight edge, okay, which is not creating the cycle. So this is the main purpose. Okay, so we are starting from 0, and initial first case we are checking for 0. So I have already mentioned 0 to 1, 0 to 3. Okay, so this we have marked as a visited. So every time we will always we will check this. We will only consider the edge which is connected between visited and unvisited vertex. Okay, this is happening in the condition in the code. So every time we will check only the edge which is connected between one side is visited vertex, one side is unvisited vertex. Okay, so why we are taking this condition? Because we not want to select the edge which is creating a cycle. If the both vertex are visited and we are selecting that edge, so that definitely that edge will create a cycle. Okay,
But
so
what is it? When the cycle will happen?
suppose this node is already visited and this node is already visited, and we are simply checking that for this edge. Okay, suppose this is the smallest weight edge and we are selecting into our final spanning tree. So this will create a cycle because we have already traversed 0 and 1 from another side, from any side. So we cannot connect this edge in our final spanning tree because definitely it will create a cycle.
Oh.
Okay, so because of that, in the each iteration we are finding out the smallest weight edge from the graph which connected between visited and unvisited vertex. Okay, so in the first iteration, so there is only one possibility because the first 0 is the visited vertex and all other remaining are the unvisited vertex, but 0 to 1 and 0 to 3 are connected. So these are the only possibility, 10 and 18. Okay, so out of these we will check another also. Okay, so we will check 1, but from 1 this is unvisited. Okay, so this is unvisited and this is visited, but this as we have already taken, so we will not repeat this. From so this 1 to 2 and 1 to 3 we cannot select because 1 is not visited and 2 is also not visited. Okay, this time both are not visited, so we are not considering this condition. So in the first iteration only we will find out the satisfied condition is for 0 to 1 and 0 to 3, 2 edge, and in that case we will select only 0 to 1 because this contains the smallest. So after that, so we will mark this one is a next v node. Okay, so not next v, we will simply repeat the same process again. Now the two vertex are visited. Okay, so now two vertex are visited, this 0 and 1. So we will check the same things from the 0 vertex. Now 0 to 1, now both side is visited. 0 to 3, yes, so this 3 is not visited, so we will consider this 0 to 3 edge with 18 weight. Now the from 1, okay, check from 1. Okay, so 1 to 2, yes, 1 to 2 we can consider because 1 is visited, 2 is not visited. Okay, so 1 to 2 is 20, and 1 to 3, yes, we can consider this is 6, Now after that we will check from 2. Okay, so 2 to 8 we cannot select because both are not visited. Now we will check from 3. So 3 to 4 we
Sir,
cannot
that
select.
one, two, three visiting. Already three is visited. No, when we are doing 0 to 3.
No, 3 is not visited right now.
No, not right now. Before, first you did 0 to 1, then you did 0 to 3. Is that right?
Yes.
Then
So
again, when you are coming from 1 to 3, 3 is already visited. No.
no, not visited. We are simply checking the adjacent, but we marked this visited value when we are
The
okay. So
minimum cost.
yeah, when we find out the minimum cost. So we are not here. We are simply iterating a loop, and we are checking the condition. We are not marking the true at the time of checking.
Uh,
Okay. So in
no, no. Let me get it clarified. Already visited but not marked. Is it until we visit from 1 to 3? That's what you are
yeah.
trying to.
So just see the implementation when we are marking true. So
Where
you
are
can
we
see
marking separate?
here. Okay, so you can see this part here. Only one time we are marking after completion of this loop. So this nested loop is actually checking the each edge in the graph.
Okay.
Okay,
So
after yes,
the
yeah, after
marking is
complete.
for
Hmm.
the bottom marking is to really reflect what I was asking. Is that right?
Which one?
The visited next V is equal to
Yes,
3. Oh,
yeah. After finding out the vertex which is connected with the source, after finding out the minimum weight edge, then we are marking the next v equal to true.
okay.
So,
Okay,
so, so
only one
that
time.
means when you're starting with you could have two or three choices, but the only one which is you may have you V1, V2, V3, right?
Yes,
Whatever has the lowest distance, you're going to
That
select
would be
that one, and then that will be updated. Other two or three you considered that's not still marked as visited,
yes. So because we
Hmm.
are comparing this condition every time,
right?
so this because of this condition, we will finally we will find out the smallest weight edge.
Correct. So only
First.
one is marked, others are
Yes.
ignored. That's
Yeah.
I think that's the critical part.
Yeah. Okay. So this is happening in the so in the second iteration actually we will find out so 3 times the condition is true, and for these 3 times we are finding out that this 6 is the smallest weight. So so here this 1 is u and this 3 is v. Okay, next v. So we will mark this as a visited. Okay, now this become visited node. Okay, at the time we are also storing this edge information. So 0 to 1 we will store in our list, 1 to 3 we will store in the list. Okay, so now the third iteration. Okay, so third iteration we will check the same things again. So now this become this is visited, 3 is visited. Okay, from 0, so 0 to 1 you cannot select. Okay, because you have already marked this 0 to in our spanning tree. Okay, so 0 to 1 is already selected, so this cannot be selected again. Okay, and 1 to so 0 to 3. Okay, so here 0 is already visited, 3 is already visited. If we mark this edge, so definitely it will create a cycle. Okay, because of that we are not selecting this. So 0 and 3 we will also not include this, and 1 to 2, yeah, we will include this. Okay, so 1 to 2 with 20. Okay, we will include in our test checking. Now 1 to 3 we cannot include, and 2 to 4 we cannot include because 2 and 4 both are not visited. Now 3 to 4, yes, 3 to 4 we can uh, we will check. 3 to 4, 3 to 4 is 70. Now in this next iteration we are only finding out 2h, now which contains the smallest 20. Okay, so 20 is connected, so now this time this is u and this is v. So we will mark this as a visited node, and we will consider this edge 1 to 2 in our spanning tree edge. Now this become visited. Same process we will repeat one more time. Okay, so 0 to 1 we cannot select, 0 to 3 we cannot select, 1 to 2, 1 to 3 we cannot select. Okay, 2 to 4, yeah, 2 to 4 we can select. 2 to 4 is 8, and 3 to 4. Yes, we can select 3 to 4 because one is visited, another is not visited. So 3 to 4 is 17, 70. And now no one is remaining. Okay, so only these are the options. So 8. Okay, so this will be marked, and this 4 we will consider as a visited. Now our process will be stopped, and you can see this is these are the edge will come in our output. So 0 to 1 and 1 to 2 and 1 to 3 and 2 to 4. Okay, so implementation can be different. So this is same things we are doing, okay, according to the Prim's logic, but implementation may be a little bit different. Okay, so maybe another implementation is also given for this in the notes.
Sir, how we can use the distance that was used in first part?
So this is the second implementation. I think we are using distance. Let me check. Yes, here.
And sir, the first problem is not opening. There is some issue.
Where? On the
Uh,
C?
the on the Replit portal, sir. Every problem is opening except the first problem.
Let me check. No, this is working fine.
Sir, I don't know for my PC, all problem are opening second, third, but first is not opening. It is just
Just refresh the
working.
page.
I press
Maybe
Control Shift R also. Hard refresh also.
no, I'm also opening this problem in our incognito mode. So it is opening fine.
Someone from the this chat could confirm that for them is it refreshing? Means after refresh it is opening.
Yeah, it is opening. Week 5,
Uh,
problem 1.
you can see how many are working in the problem number 1. Okay. So problem
Opening.
1, problem 1, problem 1, 1, 1. 5 are working on the problem number 1.
Maybe it
Okay.
just open honestly, not working yet.
Just refresh the page. Okay, so this is the different another implementation. You can see here we are just, using the same approach which I explained before. Okay, in finite we are assigning visited distance, neighbor. We are assigning simply these three dictionary, and we are maintaining. Initially, we are initializing with false, infinite, and -1. Okay, so this neighbor actually we are using for where we are coming from. Okay, at the time,
It's
like a
opening for
like a
me.
parent, like a parent.
Oh, program one is working. Opening.
Yeah, opening now. Okay. Okay, so this is the another implementation of the same prims. Visited v distance, we are maintaining this information. Initially, all are false, infinite, and -1. After that, we are starting from 0. And from 0, now this time we are repeating this process for the total number of vertices time. And in this process, we are selecting the minimum distance first. Okay, so we are finding out the minimum distance. This time we are maintaining the distance on the vertex. Okay, so you can see initially all are infinite distance. Source distance we have updated 0 by 0. So this 0 value will come in the first iteration min dist. Okay, and after that finding out the minimum distance value, we will check which vertex contains the 0 value distance. Okay, so there is a possibility more than one vertex contains the same distance value. So because of that, we are iterating the all vertex and checking the distance which are not visited. Okay, which are not visited, and we are finding out the list. So this next v list, actually this is a list. It can contain more than one vertex which have the same min dist value. After that, we are selecting the minimum label vertex. Suppose we are finding out the vertex 0, 3, 5. Okay, which contains the 0 value in the first iteration. Okay, so we will select the 0 label. Okay, so 0 is the smallest label of the vertex. So here we are selecting the smallest label of the vertex which contains the minimum distance, and then we are marking true. Okay. After that, what we are doing, we are simply repeating the same process like a Dijkstra algorithm. We are checking the adjacent vertex of this next V node which we have selected, and if not visited, okay, so if our adjacent node is not visited, then we are checking the edge distance. If this edge distance is less than equal to current distance of the V, okay, from U to V. So if this is smaller, then we will update distance V equal to D, and at that time we are updating this neighbor of V equal to next V. This is similar to parent. So if we are getting smaller distance, so from which node we are getting smaller distance, we are storing this information, neighbor. Okay. So we will repeat, yeah, neighbor list. Okay, yeah, this is the neighbor. So we will repeat this process until all the vertex are visited. So after that, we are returning this parent dictionary, and you can see this information. So which is the no, so parent of 0 is -1 because we are starting from 0. So based on this parent information, we can create a tree. Okay, so 0 is the first node because there is no parent. Who is the parent of 1? We can see 0. Okay, so we can connect 1. And who is the parent of 2 is 1. We can connect 2. And who is the parent of 3 is 1. Okay, so 3 is also 1. Who is the parent of 4 is 2. Okay, so here 4. So we are getting this is a spanning tree.
So in the previous implementation, we are storing the edge. Here we are storing the node,
Parent.
basically, like the link, basically like the parent, all
Yes.
the edges and its parents. I mean, all the vertexes and its parent vertex.
Yes, parent vertex. Parent vertex where we are getting the smallest distance.
The Prim's algorithm, is it?
Yeah, this is also a Prim's algorithm, but the way of implementation is different.
How do we differentiate these two? Both are Prim's algorithm.
Yeah, this is the way which I explained before of the previous, the first time which I explained.
How do we choose the right thing?
So you can see what we are doing. Okay, let me explain in the graph.
How do we really start working either on the edges or on the...
1 second. So this is a graph. Okay, what we are doing, we are simply assigning G. Initially, all are infinite. Okay, like this, and initially, so for we are also maintaining one information for distance. Okay, so distance for 0, 1, 2, 3, and 4. So this is distance, and we are also maintaining one another information for parent. Okay, so the NBR name is given. Okay, so like parent, we are like this. So for each node, okay, so 0, 1, 2, 3, 4. Okay, so initially all distance are infinite, and parent are -1 initially. Okay, and visited, there is one more information we are storing, visited. Okay, so visited for each node, 0, 1, 2, 3, 4, like this. Okay, so all are false. Initially all are false. So these three information we are maintaining during the process. So what we are doing, we are starting from the 0. Okay, so we are starting from 0 and we are assigning 0 distance for the 0, and okay, so this is the first step. So 0 distance, so we are updating this as a 0. So this is the first step. After that, what we are doing, we are simply traversing all the distance value. What is the minimum value? So you can see 0, infinite, 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 infinite. We have 5 vertex here. So what is the minimum distance value here? 0. Okay, so in the first iteration, we are finding out the min dist equal to 0. For the safer side, we are also checking that which vertex contains this minimum distance. So there is a possibility if the more than one vertex may contain the same minimum distance value. So because of that, now we will iterate once again, and we will check how many vertex are contains this zero value, minimum distance value. Okay, so now you can see 0, infinite, 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 only one vertex 0 contains the. So this is the another list we are getting. Next we list. Okay, so only we are getting one vertex that contains the minimum distance value 0. Okay, now after that what we will do, we will simply check the what are the adjacent of this 0.
Sir, sorry to interrupt, sir. Could you please refresh for problem number 1, sir?
Not opening.
No, sir. Every problem is opening, but that is not opening, sir.
No, I have what.
I don't know, sir. I tried incognito mode, other browsers also. Also other device, it is
Okay,
not opening.
what error is coming?
No, this is just showing the working, and on console it is just showing the booting repel. If you want, I can share my screen.
Okay, can you share? So maybe it will take some time, little bit, maybe 2-3 minutes.
Sir, it has opened first time. I tried, but after refresh, it was just working and it was not showing.
Okay, can you share?
Yes, sir. Just I am login from Google. I am sharing.
Okay. So till now, so in this process, after that, after selecting this vertex, okay, so out of these all vertex which contains the minimum distance, we will select the minimum level vertex. Okay, so min level vertex is 0 now. Only we have only one vertex, so we will select this. So now
Sir, is my
from
screen visible now?
yes,
Sir, it is just showing like this, sir. It is not happening anymore.
no, wait, no,
Okay, sir.
wait for some time.
Sir, for other, it is just opening. If you want, I can show in new tab.
No, no problem. Just wait for some time. Don't close because it is taking some initialization part.
Sir, but other problem are opening very fine.
No, maybe the type of the problems may be different. So this will maybe upload will take some time.
Just look at your CPU and RAM. Is the load too much?
What?
The CPU and the RAM, memory and the
CPU?
yeah, on the left hand side you see, right, CPU and RAM. It looks
On
like
left
it's
hand,
yeah,
on right hand side, it is battery percentage.
no,
No,
I'm
no,
talking
no.
about on the replet. Because so what's happening is it's assigning a virtual machine. It's creating a like a kind
But
of
just see, no, just I am copying this side and I am opening here. For every problem it works. Let's say this second problem. It just got connected and loaded. But this is not opening. Also, sir, I tried incognito mode.
Okay.
Initially, in starting, it got opened.
Problem 1. Copy project. And the same BBC chain. Chain. Not. Uh, just wait for 5 minutes. Maybe it will update. Okay, don't close it
Yes.
and we just wait for.
Okay, sir.
Okay, so in this implementation, so we are selecting the vertex which contains the minimum distance, and then we are checking the adjacent vertex. So in the first iteration, we are selecting 0. So now we will select this 0, and at this time we will mark as it.
Sir, you have to
Uh,
share your screen again because it got
my screen is not visible.
because you were sharing earlier student, so your
Okay.
screen is not visible now.
I stopped sharing.
Yeah,
Okay,
but
I'm sharing
you have
again.
to share
Sir,
again.
maybe if you off and on again, the first problem may be visible.
Now I've refreshed, and this problem is opening for the others, no? So I think there is no problem from our side. So if it is not opened, just tell me. I'll create another copy of the problems. Okay.
Yes, sir, it has not opened yet.
First try. So just wait for some time. Okay. Now my screen is visible.
Yes, sir.
Yes, sir.
Okay. So in the first iteration, we will check from 0. So 0 to 1 and 0 to 3. There are two adjacent possible for 0. And now we will update the distance. So the same things we will perform here. So 0 to 10. Okay, so 10 we are getting, and the previous distance is infinite. So if we are getting smaller distance, so 10 is smaller than uh, this infinite, so we will update this distance of 1. Okay, so this distance is here. I am updating 10. At the same time, okay, when we are updating this distance, we will also maintain the parent of this 1. Okay, so who's the parent of this 1 is 0. So in our next dictionary we will maintain this information. So parent of 1 is 0. We will update these things. Now from 0 to 3. Okay, so 0 to 3, yes, previous is infinite and now current is 18. So current is 18. Now we will update this 18, and if we are updating because we are finding the smaller one, so we will once again update the parent of 3 is 0. So parent of 3 is now 0. We will update here. Now this is the first step. Okay, now we will repeat the same things once again. We will iterate the all vertex which are not visited. Okay, so the first step only the one vertex are visited, 0, and we will check for the remaining vertex. Okay, so 1 2 3 4. Okay, so now this is visited, so we will not check for this. So okay, so 3 is also updated. Okay, 18. Okay, so which one is the minimum? Okay, so 10 infinite, 18 infinite. So which one is the minimum? 10. Okay, now we will check which vertex contains this smallest distance, 10. Okay, so only one contains this smallest vertex. So in the next iteration, now the value is 10, and we will get the list where the only one vertex contains this 10 value, and after that we will finalize this. The minimum distance vertex is 1. Okay, now that means we will check from 1. So the adjacent nodes of the 1 which are not visited. Okay, so 1 to 2, because 1 to 0 we cannot take because 0 is visited. So 1 to 3 we can check, 1 to 2 we can check. Okay, so 1 to 2, what is the edge distance is 20, and what is the previous distance is infinite. Okay, so we will update this 20. Okay, so this will be updated 20. Okay, and where from we are getting this 20 onto 1, so we will update this parent information here, and same things 1 to 3. Okay, so 1 to 3 is 6 and previous is 18. So previous is 18, now we will update 6, and what is the parent of 3 is now 1, so we will also update the parent of 3 now 1 here. Okay, so 10, this is done, this part is done for the this one vertex. Okay, this is now visited, so this is now visited. Same thing, we will repeat from the remaining. So now only 2, 3, 4 are unvisited vertex. So now this is visited. So 2, 3, 4, 26 and infinite. So which is the minimum? What is the minimum distance? 6. And which node contain this minimum distance? 3. Okay. So that means next is 6, and only 3 is the vertex which contains this 6, and we will finalize this as a 3. So now we will check from 3. So 3 to 0, because 0 is visited. Okay, so we will not consider this. 0 to 3 to 1 we will not consider. Now 3 to 4 is the only choice we can consider. So 3 to 4 we are getting 70, and previous 4 is infinite. Okay, so it will update by 70. So here we will update 70, and the 70 on 4 we are getting from 3. So we will update the parent 3. Okay, now this part is done. Now we will mark this as a visited. Okay, now this is visited. Now we have only 2 and 4. Okay, so 20 and 70. So which is the minimum distance? 20. So 20 is the smallest distance, and only 2 what is the vertex which contains this smallest distance, 2, 20, and we will select as a final vertex for the checking. So now we will check from 2. Okay, so 2 to 1 we cannot check, 2 to 4 we can check. Okay, so because 2 to 4 is not visited. So 8 and previous is 70. Okay, so we will update by 8 here, 8. And what is the parent of 4 now? Because we are updating the distance, so we will update the parent also. So this is now 2. So yes, so this is done. Now this is visited. Now only this is visited. Now only 8 is remaining. Okay, so 4. So from 4 there is no adjacent available which are not visited. So our process is complete.
Sir, the fourth parent is 2 and 3. How do you resolve that one?
Parent of 4 is
2 and 3 also there. No.
no. We are only maintaining one parent. We are updating every time.
How,
If we
how,
are
to,
getting
how to choose it among the two? What is the right one? Is it 2? Because the
no
lowest
minimum distance.
minimum
If we are getting minimum distance, then
take
we are
it.
selecting the parent.
Okay.
Previous when we are checking from 3, so at that time we are updating the 70 by the infinite value. Okay, so infinite 70 is smaller than infinite. Because of that, at that time we mark that the parent of 4 is 3. But after that, in the next iteration, we find out that we are getting 8 value from 2. So 8 is also smaller than 17.
Yeah.
Okay, so because of that, we are also updating the distance as well as the parent.
Okay. Right.
Okay,
Thank you.
so fine, after completion of this iteration, you can see what are the parent of each node. So the parent of 0 is -1. Okay, -1. Parent of 1 is 0. Okay, parent of 2 is 1. Parent of 3 is 1, and parent of 4 is 2. So this is the information we are getting, and this parent is are coming from the smallest distance value. So we can create the minimum spanning tree using this parent information. Okay, so that means g -1 means there is no parent. Okay, and what is the parent of 1 is 0. Okay, so 1 we can connect by 0. What is the parent of 2 is 1. Okay, so we can connect 2. 3 parent, okay, so parent of 3 is also 1. And what is the parent of 2 is 4. Parent of 4 is 2, like this. Okay, so 0 to 1, 1 to 2, 1 to 3, and 1, 2 to 4. So this is the spanning tree of the original graph. Okay, so we are finding out the edge basically. So this is the another implementation of the frames. Okay, so you can choose any implementation using which you are getting the correct answer. Okay. Okay, so next is the same Kruskal algorithm. So this is the Prim's algorithm, and another algorithm is Kruskal algorithm. So what is the approach of Kruskal algorithm to find the same things? Okay, so
So
minimum.
now it got opened just now, sir.
Okay, yeah, so it is taking some time for the initialization like this. Okay, so now the another implementation is Kruskal algorithm. Purpose is same things we will find out from this algorithm also, but the approach is different. So Kruskal algorithm, one graph is given. Okay, and I'll just quickly give some idea. So Kruskal algorithm, basically how the Kruskal algorithm works. So first thing is we consider that all edge. We find out the all edge with weights, and we sort these edges into the increasing order of their weights. Okay, so we have now 1, 2, 3, 4, 5, 6 edge in this graph. Okay, 6 edge in this graph. Now we'll arrange these edge into the increasing order of their weights. So which edge contains the smallest weight? 2 to 4, or not 2 to 4, sorry, 1 to 3. Okay, so 1 to 3 edge contain the smallest weight 6. Okay, now next second smallest 2 to 4. This is 8. Now third is 0, 1, 10. Okay, and next one is 1 to 2. Not 1 to 2, sorry. 0 to 3. 0 to 3. 18. And 1 to 2, 20. And 3 to 4, 70. Okay, so this is the first step of Kruskal algorithm. So first we will arrange our edges in the increasing order of their weights. And after that, we will simply consider that each vertex is a separate component. Okay, so we are simply arranging this as a separate component. 1, 0, 1. Okay, like this. 2, 3, and 4, like this. So initially we are assuming that each vertex are separate component. It is not connected to another one. After that, we will simply read the edge one by one. Okay, from the minimum edge weights side. Okay, so first we will choose 1 to 3, 1 comma 3. Now we will check that 1 to 3. Okay, so at the time of connecting this edge in our final output, we will check that this edge is creating cycle or not. So there are some way to check this. We will check this thing by the implementation, how we are maintaining this information. So if our edge is creating a cycle, we will ignore. If our edge is not creating a cycle, then we will consider it. Okay, so first edge 1 to 3. If we connect this, it is not creating cycle. Okay, what is the weight? 6. Okay, now next is 2 to 4. 2 to 4, when we are checking for this 2 to 4, this is also not creating the cycle. Okay, when we are connecting this is 8. Next one is 0 to 1. Okay, so 0 to 1, when we are connecting 0 to 1, it is also not creating cycle. We will also consider this. Now this is done, this is done, this is now 0 to 3. Okay, so 0 to 3, you can see if you connect this 0 to 3, then it is creating a cycle. So we will not consider this, we will ignore. Okay, now 1 to 2, 1 to 2, if we are connecting this 1 to 2, it is not creating the cycle. So this is 20. And 3 to 4. Okay, so 3 comma 4 is 70. If we are connecting this 3 comma 4, it is creating a cycle. We will ignore this.
How will we? Okay, like DFS we'll check.
There is some way using this component information. I'll explain by the implementation. Okay, so this is the simple process how we are doing this thing. What is the concept of cross-sell algorithm? Okay, now the main part is how we will maintain this information that edge is creating the cycle or not. How we'll check this. Okay, so this is the concept of cross-sell algorithm. So this is the simple one. And finally, we are getting the minimum spanning tree. And if we add all the weights, we are getting the total cost. Okay, so this is 44. Now, if you see the implementation, so what we are doing in the cross-sell algorithm, we have the same adjacency list data structure. Now, edge list. Okay, so we are maintaining the edge list now. Component. There is one component dictionary and tree edge. This tree edge for the final output result. Okay, so here we are maintaining this component information. So this is the useful one here. After that, what we are doing, we are simply reading the all edge in from our graph. Okay, and we are storing these edge in our edge list. Okay, edge list where the first value is representing distance, comma u, comma between u and v. Okay, we are simply fetching all the edges information from our adjacency list, and we are all appending all the edges in our list in the tuple form. And inside the tuple form, first we are storing distance, and second and third are representing the vertex where the edge is connected. Okay, and after arranging the edge in this manner, we can simply perform the sort method. Okay, so here you can see we are simply applying the sort, and our all edge will be sort in increasing order of their weights. So this is the first thing, and at the same time in the same loop we are also maintaining this component of u equal to u. So I said that in our diagram initially we assume that each vertex are the separate component. Okay, each vertex are the separate component. So if we are assigning the 0, 0, 1, 2, 2, 3, 4. So that means each vertex are separate and not connected to anyone. Okay, so because of that we are maintaining this component value, value for each vertex. Okay, so 0, 1, 2, 3, and 4. So initially we are assigning the same value. Okay, so 0, the who is the, so basically what we are maintaining, we are simply maintaining the leader of the one component. Okay, we are simply finding out the leader of the one component. So here in the first time each node contains only one vertex, each component contain only one vertex, so that is the leader. Okay, so here leader of the this one component is 1. Okay, this is 2, this is 3, only because in each component we have only one vertex, so that is the leader. Okay, so after that what we will do, we will simply check the edge. Okay, so you can see we are sorting the edge. Okay, so now all edge will sort in the increasing order of their weights. After that we are reading the edge. Okay, for d, u, comma v in the edge in the increasing order, and then we are simply checking component of u does not equal to component of v. So this is the condition which is representing the if this current edge is creating a cycle or not. Okay, so how we'll update this, how we'll maintain these things. So what we will do in the graph, so initially you can see at the first time, okay, when we are connecting first edge, so initially all vertex are the separate component, so the value is also a separate. So because of that, I mentioned that we are selecting one leader in a one component. Okay, so after considering, so we are checking that what is the value of component 0 and what is the value of, so which edge we are selecting. Okay, so we are selecting 1 or 3 edge. Okay, so 1 of or 1 comma 3 edge we are selecting for the checking. So 1 or 3. So what is the component value of 1? 1. Okay, what is the component value of 3? 3. Both are different value. So that means this component value is actually representing the vertex are coming from which component. So if the value are different, that means both vertex are coming from different component. So we can connect them. Okay, so this is not creating a cycle. Okay, if the value are different, okay, so that means these components are not connected by any edge before. So we can include this edge and we can connect both component and we can create a one component after connecting. So after connecting this 1 and 3, now this become a one component. Okay, so leader should be only one for the each vertex. So now we will decide the leader. We can select the leader like 1, or we can select the leader for 3 for each vertex. Okay, so these things we can maintain by the implementation. If we are checking for like 1 comma 3, so 1 comma 3 edge, so if the component value are different or for 1 or 3, so we will check what are the what are the previous leader of the 1. Okay, so 1, and we will update this one for the each vertex, each edge, or the remaining part. Okay, so now what we will do, now this is represent 1 and 3. After connecting, this is representing a one component, so definitely one value should be assigned as a leader, either 1 or 3. So we will do these things by the implementation. So what we are doing actually, you can see, if this condition is true, then we are including this edge in our output te, and we are finding out the what is the component of u. Okay, what is the component of u, and we are storing this in c value, and we are assigning this c for the each uh, vertex of the another component. Okay, so for w in w list key, okay, so we are checking the this, so we are checking this d comma u comma vh. Okay, so we are checking what is the component of u. Okay, so suppose component of u is like u. Okay, but there is a chance this another component contains 2 3 vertex. Okay, so maybe 2 or 3 vertex. After processing 2 or 3 times, so there is a chance that another component contains 2 3 vertex, and so we will update the component value for each vertex. Okay, we will update the component value for each vertex, because after adding this u comma v, so we will maintain this information. So component value should be same for each vertex. Okay, so these things we are performing using this for loop. We are checking w in w list key, we are checking, we are reading the graph, and we are checking which node contain the component value c.
Sir, aren't we in this code updating the component value to be the whatever last component we have? So like we have 0 and 1, so probably we are assigning component
Yes, so
value.
actually if we are selecting u edge, okay, so u comma v, so the what value is coming at the 0, sorry, what value is coming at the u, we are reading the component value for this. After that, we are finding out the which vertex contains this component value c, and we are updating the component value. What is the component value of v? We are updating this. Okay, so we are traversing each vertex. You can see each vertex we are traversing, and we are checking which vertex contain the same c value, component value, and we are updating the component value for each vertex that which contain the c value, and we are assigning the component of v to each vertex.
So in this, like if we were coming from 1 to 3, we are assigning the component value as 3
Yes,
for
3
1
3.
and 3 both.
Yes, correct. So in this case, the component value of 1 will become 3, Okay, and 3 will also remain the 3 in the first iteration. Now this 1 and 3 is representing a one component. The leader of this is 3. Okay, now next cycle. Okay, so next when we are choosing this 2 and 4. Okay, so 2 and 4. Now same things we will check. What is the component of 2 and what is the component of 4? If both are different, we can include. Okay, so now you can see 2 and 4. If we are including this, so what is the component value of 2 is 2 and component 4 value is 4. So we will update the component value of 2 is 4. Okay, 4, and 4 this will also remain 4. Okay, like this. Okay, next iteration when we are including this 1 3 ho gaya, or 2 to 4 and 0 to 1. Okay, so 0 to 1. Now you can see uh, 0 to 1 when we are including. So what is the component value of 0? 0. What is the component value of 1? 3. Both are different, we can include. Okay, so we can include, and at the time of when we are including this, so we will update what are the component value of this.
Of 0.
Yeah, 1. What is the component value of 1 is
3.
3. So we will update this 3 value on the 0. Okay, now this will become 3. So that means the 0 1 3 is coming from one component. Because of that, all the value are same. All component value are same, 3 3 3. So this is the next and the next one is okay, now the cycle case. Okay, 0 to 3. So this is the cycle case. At any time, if the component value is same, that means both vertex are coming from the same component which is already connected, and if we consider this as, it will create a cycle. So this case is actually identify that the cycle is coming. Okay, if the component value are same, that means this current edge is creating a cycle. So we will not include this. So you can see in the else part, there is no else part for this condition. Okay, so else part we are not doing anything because that else actually is creating a cycle. We are ignoring this. Okay, so in the next part when we include 1 2, so 1 and 2. So what is the parent value of 1 is 3. Okay, and what is the parent value of 2 is 4. Both are different, we can connect. And when we are connecting, so what is the parent value of 2 with this one? Okay, so 4. We will assign this 4 value with every vertex of this part. Okay, because of that we are traversing. So we are simply checking that what is the parent value of 3. So 3 parent value is for 1 0 and 3. Okay, so we will update by 4. So we will assign by 4, we will assign this by 4, we will assign this by 4. Okay, so in our component table, so where we are getting 3, we will update by 4.
So there's just one confusion. Like when we are coming from like 0 to 1 or 1 to 0, like if we were coming from 0 to 1, we will assign whatever.
So this is happening based on the implementation. Actually, implementation what we are doing, we are simply checking this u comma v. So this s can be written as a v comma u also.
Okay.
Okay, so here if we are reading u comma v and we are getting 1 and 3. So based on the implementation, we are assigning the parent of this 3 to each vertex of this u component.
Okay, okay. So whatever the edges list is there, that is the order we are following.
Yes, we are following. Okay, so in that case, you can see finally we are getting the same component value on each vertex. Okay, 4 4 4 4 4. Now that means we are getting one component. All nodes are connected. So this is representing our final minimum spanning tree. Okay, I hope this implementation is clear.
So like, where are we taking the weighted weights into consideration?
Weights, which weights?
There are no weights in the Kruskal algorithm.
So because of that, here we are maintaining this sorted edge list, and we are selecting the edge in the sorted order.
Okay, okay.
Okay, and we are finding out that if the edge is creating a cycle, we are ignoring, otherwise we are including. Okay, so because this condition actually, if component of u does not equal to component of v, it is confirmed that this edge u comma v is not creating the cycle if this condition is true. Okay, uh, if we are including the edge u comma v in our spanning tree, we are updating the parent information to maintain the next level.
So when we use the sort function, so whatever in that, because the values inside that edge list are tuples,
Hmm.
right? So it will use the, so sort function uses the first tuple to sort.
Yes, so we
First,
are
okay.
sorting based on the first value. We
So,
want to sort based on the first value. Because of that, we arranged our edge in this manner.
okay. So
Okay.
because the distance value, the weight value is in the front, we do not have to mention anything else. We just have to use the
Hmm.
sort function.
Yes, yes. So
I
before
think
that, we
you're not sorting on the edge. You're not sorting on the edge value, no?
We are
no,
sorting on the distance, right? Whatever that
yeah,
distance.
based on the distance. Because of that, we shifted this distance at the first place, and we created a new list where the each tuples inside the each tuples the distance is coming at the first place. Okay,
Where
so
is the initialization of that one? Edges and the distance and all those things. Where is it getting initialized?
no, this is the
This
edge dot sort. Edge dot sort
Line
after.
number 6, right?
Huh,
So edges dot extend this edges. So line number 3, we do this edges component t equals to this.
yeah,
Then
we are
line number
list
2.
comprehension we are using actually. Okay,
So
so
the
we are,
edges, the first one is the one on which we are sorting it. That's it.
sorry, which
The
one?
sorting is based on what?
Distance.
And the distance is where it is captured.
We are reading from the adjacency list for each u. Okay, for each u we are reading the adjacent value v comma d,
So we are
and
reading
we are,
only in the if loop, huh?
So the sort function is by default ascending, right?
yes, ascending.
So where are we in the list?
No, we are getting this w list. Okay, in w list we maintain this source and comma one list u comma v. Okay, like this u comma d, sorry, distance. Okay,
Distance u and v, you know.
v comma d, not no. So u is represent the key, and v is represent by the value of the key, and inside the list, so there are multiple adjacent are possible. So in each tuple we maintain this in the form of destination vertex and distance.
Source vertex. No,
Okay,
source
from,
vertex is the key,
yeah,
huh?
yeah, from u to source vertex with distance d. In this manner our adjacency data structure contain the information. Okay, so these things we are reading from the data structure, and we are arranging into another form d comma u comma v.
Can you please scroll up, sir? The rest of the code, can you see?
This one.
Yeah. So here the edges are, huh?
One second, I'm arranging things.
What are the values here in the edges? 0, 1, 10. 10 is the weight, 1 is the source. No, 0 is the source and 1 is the destination. Huh?
No. So in edges list, we are maintaining distance at the first place, then comma source, then destination.
No, edges first is not distance, no?
No, first is distance.
0.
We are creating this list here, na? Okay, just I'm copying this code and just run the code. Okay, let's see
Okay.
what is coming. One second. Week 5. This is cross screens. Cross color. Okay, so you can see here also what value is coming. Okay, so you can see the screen.
Yeah.
Hmm. So I am running this code. Okay, so this is critical implementation, and I am running. You can see what is coming in the data structure. Okay, so this is the value. This is the W list. Okay. Okay, so where is the pointer? Okay, now this is the suffix part. I'm quickly running the complete things. 1 second. This is the initialization part, and after that we are calling critical function with the W list. So now the function is called. You can see the W list format. Okay, so W list format is. Oh my God, this is very tough. Okay, 902. Okay, so the representation is tough. 1 second. I did this code. Sorry, I read this. First, you can check what is the type of W list. Okay, so print WL. And I'm so I'm running this code. You can see the dictionary format. This is the W list, adjacency list format. Okay, so this 0 is representing the source vertex, and there are two adjacent from 0, 1, and 2. Okay, so 0 to 1 with 10 distance, and 0 to 2 with 18 distance, like this. Okay, and now the second key 1 is representing the source, and the value are representing the all adjacent of this source. So 1 to 2 with 6, 1 to 4 with 20, 1 to 0 with 10, like this. Okay, so this is the adjacency list format. It is clear?
Yes, sir.
Okay, now after that, what happened when we are creating the edge? So this is actually we are using list comprehension, and we are reading this source to adjacent vertex with distance, and we are just simply changing the order, and we are creating a new list using this list comprehension. Now I'll just quickly show what are the values coming for edge. After this edge is okay. 1 second. Print. Oh, sorry. Oh, I cannot. Yeah. So after completion of this loop, you can see what value is coming inside the edge. So you can see, so 0 to 1. Okay, so this first key 0 to 1, I am simply rearrange the order. So 10 value is coming at the first position. Okay, so this distance 10 is between 0 to 1. So first tuple is representing this information 10 distance with between 0 to 1. Second is representing 18 distance between 0 to 2. 0 to 2. Okay, so this value we are reading from original data structure and rearranging the order. Distance we are coming, so the distance is coming at the first place. Source vertex value is coming at the second place, and destination value is coming at the third place in the each tuple. Okay, so this list is coming when we are creating the edges. using this list comprehension.
And we sort them.
After that, we are sorting. Okay, so sorting will happen based on the first value. So if I write this line again after the sort, so you can see the all. Now you can see this is the next sorted list. Okay, so this is the next sorted list. Okay, so five. This is the five distance between five and six vertex. Okay, so five distance between six and five. Uh, this is something. Yeah, this is correct. Okay, and six distance between one to two. Six distance between two to one, 2 comma 1. Okay, so here actually we are getting the both edge by 2 entry. Okay, so 1 to 2 and 2 to 1, both edges is coming as it by the 2 entry, but it is not creating a problem because if we are checking this in the next iteration, if one time we are considering any edge and it is included, then second time if we are considering the same edge, it will not include again. Okay, because it is already considered. So this is happening in this code. We are finding out the all edges information from the data structure, and we are arranging in this in the tuple format, distance comma source comma destination, in this format. After that we are sorting, then we are performing this Kruskal method by the each edge. Okay, this is clear. Hello.
Yes, sir. Yes, sir. I got it. Right.
Okay.
Thank you.
Yeah, so this is the Kruskal algorithm. So just go through it once and implement by own, and then you can go. So this is the last topic of week 5. Now we can move to the problems.
So the only difference I see in primal is going from vertex to vertex, right? And you're doing it like in a very sequential way. Whereas here, it's kind of designed, it's like a bottom up, right? So you're kind of focusing on the edge and not the
Edge.
vertex, right?
Yes,
And then
correct, edge.
and it could be disconnected. There it was all kind of connected, right? There it is disconnected, and then you're trying to combine. So it's kind
Yes.
of
Yeah.
so
Yeah, correct. This is the bottom up approach. We are simply connecting the edge from the bottom side, and finally we are getting the one component. Yeah.
so we didn't discuss the complexity of both.
Yeah, you can. We can discuss. Okay, so one second. Opening the implementation again.
Anyway, we can solve the problem, but yeah, we'll discuss after we learn problem.
Okay. So Kruskal algorithm, you can find out what we are doing inside the. Okay, so first we are running the edge. Okay, so we are running the edge loop, total number of edge. Okay, so that is representing E. Okay, after that, every time we are updating this key information. For each edge, we are updating the component value of each vertex. If we are finding this edge is included, so we are updating the component value. Because of that, we are running this complete vertex. So wlist.key is representing total number of vertex. Okay, so we have to check for each vertex. So you can see we are getting this edge dot sort e log e. Okay, e log e for the this sorting, and from here we are getting e into v. Okay, so which one is the highest value? So we can represent this complexity e log e plus or ev, maybe 1 second. I think this is written somewhere. Let me open the slides. Explanatory. Yeah, so this is the Kruskal algorithm summary. Complexity is n squared due to naive handling of the components. Okay, what n square is here? Okay. Yeah, so this is n square. Okay, so n is actually we are representing this number of vertex. Okay, and our total number of edge will be n minus 1.
Yeah, so that's
Okay, so more than that. Actually, we are traversing more than that this edge. Because of that, we are finding this complexity n into n square.
so because I think we are incurring that cost of calculating the minimum, right? If there is some better data structure, I don't know, maybe we'll save some.
Yeah, so that we will discuss the same algorithm in the week 6 also, where we will improve this algorithm, Kruskal algorithm.
Yeah, because we saw like n square is not a good option. Anytime we see n
Yes,
square
correct.
means it's not acceptable. So we have to get to n log n or something like that.
Yes, correct. So we will just reduce this part. Okay, this component update part actually. Okay, where is this? Yeah, here. So actually, what happening is Kruskal algorithm. Every time we are updating the component value because of that, and we are traversing each vertex to update this. So is there any way so we can do these things in the efficient way? Component.
If we can get that minimum thing in order one, then it will solve it.
So
That's
there is one way. So what happened? Suppose if we have two component, okay. So one component is contained like one value and two value, okay, and another component is contained like 10 value. So like 3, 2, or like this, and 10 like this. Okay, so 8 value another component, and we are checking the next as 1 to 3. Okay, we are adding this 1 to 3 edge. So which part we should update actually? This contains only 2 nodes and this contains 8 nodes. So how we can improve our steps? So if we find out the parent of this big part, okay, and we will update the parent value for the lower part, okay, which contains the smaller number of nodes. So we can save our this process time if we can find the size. Okay, so another way is we are reading the parent of this smaller part. So what is the parent, what is the component of this smaller part, like 2, and we are updating this component value 2 for each node of this bigger part. So this will take last time. So instead of this, we will find out the component of the bigger part and we will update on the smaller one. So this is the one way to improve this algorithm.
got it, sir.
I didn't really get the discussion.
No, this actually will come in the week 6. So
Okay.
right now, just focus on the week 5 Kruskal algorithm implementation. So week 6, we will just discuss the improved version of Kruskal algorithm as well as the Prim's algorithm. Okay. So now let's see the status of problems. Oops. Okay. So problem number 1, only 2 have solved. Submitted. Many of you have submitted, I think so. Number should be increased. Yeah, so 5 is submitted. Problem number 1, 2 is also done. There is someone. 3 is also done. Okay. So let's check the problem number 1. So anyone want to explain the solution or approach?
The simple approach, sir. I
Uh,
have used the Prim's algorithm, sir.
okay, Ritik, have you done?
Yes, sir.
Ritik, this one. Yes. But you not submitted the solution.
I have resubmitted again, sir.
Okay. Yes, correct. So the problem statement is just quickly read this problem statement. So problem is straightforward, not too much stories involved. Mostly in the graph problems, actually you will find out the story, some story. Okay, so you have to figure out that what are the things we need to figure out from the story and what algorithm is used for that. So here the story is smaller one. You can simply figure out that an airline company want to make airport to connect n city level from 0 to n minus 1 all across the country. The active function airport distance map that accept a weighted adjacency list distance map in the following format. The function returns the minimum distance of airport network of to connect all n city. So this is straightforward. We are simply finding out the minimum cost of the spanning tree. Okay, minimum cost spanning tree, and we want to return the total minimum cost value. Okay, simply applying any algorithm, either Prim's algorithm or Kruskal algorithm, you can simply write and pass this data structure, uh, uh, this map, distance map, and that algorithm will directly return the cost value. Okay, so you can write either Kruskal algorithm or Prim's algorithm. So here in the code, which algorithm is used? This is Prim's algorithm. Yeah. So Prim's algorithm, you can see this. This is the Prim's algorithm. Here we are using. This is Prim's now. Ritik? Yes, this is Prim's. Okay. Yesterday. Yes, this is Prim's. Yeah. So you can see the Prim's algorithm we are using. Simply we are writing the same steps of the Prim's algorithm, and the we are maintaining this wasted and cost. Okay. So here we are directly using this cost value, and at anytime we are getting the smallest distance. Okay, and we are adding this smallest edge weight into our cost. Okay, so if you know the implementation of Prim's or Kruskal, you can directly use that algorithm. So I think no need to explain the Prim's and Kruskal again. We have already seen this. So nothing extra is required to solve this problem. Okay, directly written the complete Prim's or Kruskal algorithm here, and you will get the answer for this. So problem 1 is not tough. So we can move to the problem number 2. If someone have any doubt in the problem number 1, you can ask. Yeah, problem number 2, Siddharth is done and Kabir. Anyone is there in meeting? Siddharth or Kabir?
No, sir, I didn't finish second one.
So I'm opening the Siddharth one. And let's check. Oh, the implementation is not correct. Okay, let's check the another implementation. Kabir. Yeah, this implementation passing the test case. Okay, let's read the problem statement and let's see what approach is required. Okay, so you are given a network of n nodes labeled from 0 to n minus 1. You are also given travel times. A list of signals travel times is as directed as travel times I equal to ui comma vi comma wi, where ui is the source node, vi is the target node, and wi is the time it takes for a signal from to travel from source to target. Okay, write a function mean transmission time and travel. Okay, so that accept number of nodes n and list and the source node s to send the signal. Okay, so here we are sending the signal from source node. The function returns the minimum time required for the signal sent by the source node to be received by all the remaining n minus 1 nodes. If it is possible to obtain a signal for all n minus 1 nodes, return.
Sir, excuse me, sir. Sir, sorry, sir, I got disconnected, sir. What have done from then?
No, I just quickly visit the problem number 1. Okay,
Okay,
so I think only the simple straightforward any one algorithm we can use, either Quetzal and Prim's algorithm. So now I'm just quickly visiting the problem number 2.
okay, sir, got it.
Okay, so if you have any doubt in problem 1, you can ask. I
No
think you
doubt, sir.
you have
No.
already completed, so I have explained from your code.
Yes, sir. Yes, sir.
Mhm. So problem number 2, have you done?
No, sir.
Okay. So this is the thing. Here we are asking the minimum number of times required to reach the signal for every destination. Okay. So if signal is not reaching to any vertex, then in this case we will return -1. Otherwise, we will return the minimum time required to receive the signal by every vertex from source. So can anyone explain what approach is required, what algorithm is required?
Sir, longest path.
Longest path. Okay, so you are saying that if we find out the longest path value, then it will represent the minimum time.
Yes, sir. Because that path we have to at least travel once.
Okay, so longest path means from source to any destination which contains the longest path value. Correct?
Correct, sir.
Okay, yeah. And which algorithm we can use?
DFS, sir.
Yeah, you can use DFS or Bellman-Ford, any algorithm you can use. So the purpose of the both algorithm are same. So not DFS, dashed algorithm.
Yes, sir. Yes, sir. Right.
Yeah, dashed algorithms or Bellman-Ford. Okay, so here we will find out the shortest path from source to every vertex. Okay, and in this shortest path value, what is the maximum value? We will check. So we will return that value. If any value is infinite, okay, if any destination value is infinite, so we will return -1. So the approach is also easy for this. So here we have one graph, and the graph contains the weights or anything. So like 0. So this is like a directed graph like this. Okay, so 10, 5, 3, 2. like this. Okay, so now we have given this source vertex. Okay, so this source, and this source is actually sending a signal. Okay, and what is the minimum time required? So where the each destination another vertex, okay, from the source, any remaining, all the remaining vertex should receive the current signal. Okay, so this is 10 5 is actually representing the time from 0 to 1 and 0 to 2. So simply apply the shortest path algorithm, Dijkstra algorithm. You can apply single source shortest path. Okay, so we have only single source, and you can apply any single source shortest path algorithm, and after that you can find out the minimum distance, shortest path distance from the source. Okay, so 0 to 1 what you are getting. Okay, so 0 to 2, 0 to 3, 0 to 4, and 0 to 5. So what distance you are getting? So after that, all distance like A, B, C, D, E. So these all are the shortest path distance. Okay, so 0 to 1 and 0 to 2, these are the all shortest path distance. And it is representing the minimum time required to reach the signal from 0 to 1, 0 to 2, like this. After that, we will select the maximum value among all these value. So that is the time actually required where when the all remaining vertex are receiving the signal, at least. Okay, so this is the way to solve this problem. And there is one more condition. If we are initially we assign the 0 at the source vertex and infinite at the remaining vertex in our shortest path algorithm. If we are getting infinite value on any vertex, that means that vertex is not reachable. Suppose this connection is looking like this opposite. Okay, so 5 to 3 and 5 to 4. So now 5 is not reachable from 0. So in that case, you will get the infinite value on 5 from 0. So just return the minus value if any vertex are not receiving the signal. Okay. So just read all the value. If any value is equivalent to the infinite value, just return the minus one. Otherwise, return the max of all among all the remaining value. So this is the approach. I think this is also a straightforward approach. You can use Dijkstra algorithm or Bellman-Ford algorithm for this. So what we are using, I think Bellman-Ford. Yes. So you can see this implementation. It is written by Kabir. So also comments is also there. So what we are doing, create a adjacency list to represent the graph. Okay, so we are creating a adjacency list, and this is the part of adjacency list we are maintaining. Yes, so distance initially we are assigning the infinite value. Okay, so in this way we can represent the distance infinite value for each vertex. So in this line we are assigning infinite distance on each vertex. After that we are assigning distance value for the source is 0. Okay, so we are performing the same things of this single source shortest path. Then we are performing Bellman-Ford algorithm from the source S, and this using this Bellman-Ford algorithm we are getting the shortest distance for each vertex. Okay.
Just a question, like how are you doing it for like the distances above the? Can you like scroll up a little?
Above the
Just scroll up a little, like in which we were doing the distance equals float I and F. Yeah,
Mhm.
in like this asterisk and
Yes.
initialize distance array with infinity values. So
Mhm.
this because like we are not mentioning.
So it is creating the infinite value for each vertex from 0 to, so n times actually. So n times means 0 to n minus 1 vertex. Okay, so here vertex value is given how many vertex we have n. So we are assuming that our vertex level is starting from 0 to n minus 1. So this actually distance list is here we are creating a list where the each index is representing a vertex name and value is
Okay.
representing a distance.
So because we do not have to use a dictionary because our okay.
Yes, so you can also use the dictionary. Okay, so in this implementation, Kabir is using only list, Python list.
Sir, this is Siddharth.
Yes, Siddharth.
I have used the Dijkstra algorithm, but I am
Okay,
not getting all cases passed.
okay, okay. So yeah, initially I open your code. Actually, I saw that.
I got disconnected in between.
Okay, okay, okay. Let me open your code now. So this is the simple approach we can use. We can use Dijkstra and Bellman Ford. Yes. Week 5, week 2. Siddharth. Okay, so Siddharth, this is your implementation,
Yes,
and you are using Dijkstra algorithm approach.
yes, yes.
So are you sure your Dijkstra algorithm approach is correct?
Dijkstra should work because the edges are not negative because the time cannot be negative. No, so
Yes, yes. No, no, implementation is correct. Dijkstra implementation.
I think so, sir. I mean,
Okay. So what you are doing here, NHS. Okay, so you are creating dictionary. Oh, what is this? IDGA. Yes. What is S? Okay, source. What you are doing in this part? First 3 to 8.
I'm trying to make a dictionary out of the list because traversal of the list every time is very difficult, and so I'm making a dictionary out of this list.
Okay, adjacency list you are creating.
Yes, yes,
Correct?
yes.
Okay. Okay. So okay, so you are reading H. Okay, so I think you are not creating all keys in the dictionary.
Okay,
Okay, suppose no edge is going from the any vertex from the graph, and that means that that should contains the empty list.
okay,
Okay, so like in this graph you can see if I am reaching from 3 to 5 and 4 to 5, now the 5 value should also be there with the empty list.
okay,
Okay, so first create a dictionary with the list for the each key. So here the vertex value is given n total, we have n vertex. So create the key for 0 to n minus 1 with the empty list. After that reach this edge, read this edge and append in your existing list
okay, okay, okay.
in that way. Okay, so because of that this maybe error is coming. Okay, so once your digital approach is correct, then it will work for definitely. So last thing is max I equal to 0. Okay, for I equal to in 8. Okay, still you are not checking these things infinite.
Infinite, yes, sir. Here I have checked if mean distance equal to infinity, return minus 1. 18 line number. 18 number line.
Okay, okay. Line number 18 here.
Yes.
In dashed algorithm, you are doing this.
Yes, yes. Because if one of the node is not reachable, so the mean distance will be infinity in that case. So one of the node is not reachable, then, and I'm getting those results. I'm getting past where it is to be minus one. I'm getting minus one. Only cases where I'm not getting minus right answer is the ones in which there is a number.
Okay, okay. Yeah, approach is looking correct. If this value is coming as a -1, yeah, correct. So you can return -1. Hmm. So it should work, yeah. So are you updating this?
I was listening to you, sir. Now I'll try to do it.
Okay, okay. Yeah, others, any query in this problem? Problem number 2. Any doubt?
Sir, now I am passing all the cases.
Oh, you have updated?
Yes, I am passing all the cases now.
Yeah, correct. Yes, so this is the only thing. Yeah, another can see this implementation also. So here we are using this dice algorithm. So initially Siddhartha is creating an adjacency list from the edge. Okay. So this adjacency list should contain all the vertex as a key with their adjacent value. After that, we are applying simply dasta approach. Okay, so initially all are the infinite, then we are maintaining this visited value and distance value, and we are performing this dasta algorithm. So dasta algorithm will return a distance, okay, dictionary, this distance dictionary for which is representing the shortest path from the source vertex, and then we can simply reading this distance value for each vertex, and we can check if we are getting infinite value for any vertex. Okay, so we can return -1, otherwise we can return the maximum value of the distance. Okay, so in that way you can solve this problem number 2. If you have any query, you can ask anyone. Okay, now move to the problem number 3. Okay, now Kaveri is done. Tejas is done. Let's read the problem first, and then we'll see the solution. Okay, so this is the problem. An airlines company has flight operation in n cities level 0 to n minus 1. Try to function best fare. Okay, so some details is given in the data structures in which you are given a weight adjacency list flight route. Okay, so this is adjacency list data structure. What is required, you are also given three integers: source, destination, and k positive integer value. Okay, so source value is given, destination is given, and k value is given. And this k, what is representing? K is representing minimum number of stops required in between the source and destination. Okay, so function return minimum cost and flight route in the format minimum cost, comma source. So this is the format of route. So source should become, then next stop, then next, and then destination, in that way. Okay, so from source to destination with at most k stops in between, so not included. Okay, so yeah, with minimum number of k stops.
Sir, I think Bellman Ford will work, and we need to stop somewhere in between in case after K iteration.
So some data is already given. There is one code is given in this problem, which actually returns the all path. So you no need to use any algorithm in this. After getting all the path, all the possible path, you need to find, you need to use your own logic. Actually, you need to figure out the path which contain at least k number of stops in between minimum, and out of these path which contains the minimum cost. Okay, so here some code is already given. Just use this and read all the path, and out of these all paths just check which path is
Sir,
useful for
what
them.
type of path it will give, sir?
All possible path from source to destination. So suppose if you have a graph like this, so A to B to C and to D. Okay, and one is like E to D. Okay, one is E to C to D. Okay, so if source is given as a and okay, destination is given as a D, so how many paths are possible here? So you can go through A, B, C, D. Okay, so this contains two stops in between. Okay, and AED, okay, it contains one stops. AECD, okay, so it contains two stops. So all the paths out of these all paths, suppose the k value is given as a 2, okay, in the problem, and source is A and destination is B. So the given suffix code, okay, will return all the possible path. Okay, and out of all these possible path, you need to check the path which contains at least two stops. Okay, so sorry, not at least, I think at most.
We have to select only those paths.
Hmm.
So we
Uh,
will just count the lane and then we can return based on that.
yes, yes, Tommy. Okay, so this is the thing. At most, I think. Okay, with at most k. Okay, so at most k, not the at least.
So there
Okay.
will be multiple paths, and we will see his list and count by lane. And if
Yes.
it is within, then we will append, and after all append, we will return.
Mhm. So in this case, suppose k value is given 2, okay, and now you will get all these three paths, all are satisfying the condition. Okay, so here the stops number of 2, and you need to find out the path which contain at most two stops. Okay, so this will also consider, this will also consider, this will also consider. So suppose the distance is this for 50, and this is for 60, and this is for like 40. So you have to read all the path, and you will figure out that which is the smallest cost, and you need to return this cost, minimum cost, and with path also. Both values should return. Okay, so there is no need to find out the path. That code is already there. Just read the output, and after that you need to compare the distance of each path which is satisfying the problem condition. Okay, so let's see the solution of the Kabir. Yeah, it is passing the test case. Okay, so I quickly explaining the solution of the Kabir. Okay, so the error code is already given. Now the you need to write the only this best fair part. Okay, so what we are doing, we are simply receiving all the paths using the above code. Okay, so we are calling the above function and with the required information, and we are getting all the possible path in the list L. Okay, if this list is if does not equal to 1, what is this one represent? If L does not equal to 1, or okay, so I think this one, I don't know why this one is taken, but we can write also if list is not empty like this. Okay, that means no path is available. So if list is not empty, then we will check these things. So we are finding out the cost. This cost is okay, infinite, I think. Yes. So this cost value actually we are calculating as a infinite value initially. After that we are figuring out the root and in the all path. Okay, so in the all path of the list, we will check the length of the path. Yeah, so this if the length of the path is less than equal to k plus 3. Okay, so k plus 3 means we are including a source and destination value. Because of that we are assigning this k plus 2, and we are using this sign is less than, so because of that we are using this k plus 3. Okay, if our path contains the length is less than equal to k plus 3, or we can write this less than equal to k plus 2, so we will consider only that path. Okay, if any path contains more than the this value k plus 2, so we will not consider that. Okay, so this is satisfying our at most condition of the k, and we will check the only for those paths which is satisfying this condition. After that we are simply checking the cost of the path. Okay, so to check the cost of the path, we have to use our data structure flight route, and based on this path. Okay, so path value is given like 0 to 1, then 1 to 2, like this. So in this case we will find out the what is the cost value is assigned as the 0 to 1 and 1 to 3, like this. Okay, so we are reading this value from our data structure. So for I in range 0 to line path is, and for j in flight route, and we are reading this. If path of I plus 1 equal to j, so we are checking this. Okay, yeah, we are checking this information path. What is j in flight route path of I? Okay, path we are reading here. J of I. Sub. Okay. For j in flight path. Okay, this is adjacent. I plus 1. Okay, okay, got it. So actually we are reading the path value. Okay, so suppose the first value of the path is 0. Okay, so we are reading this 0 value, and now in the next loop we are checking this, what are the adjacent nodes of this path of I. Okay, what are the adjacent node of this 0, and in this adjacent nodes are we getting the next path value. Okay, so 0 to 1, so 1 is coming in the adjacent of 0 or not. So if this is coming, then we are reading the distance value, and we are adding in the cost. Okay, so we are simply finding out of like this. I'm explaining in the notepad.
Sir, what happened in this loop? I didn't understand.
Yeah, I'm explaining in the graph here. Okay, suppose I'm getting the path like this. Okay, so our algorithm is returning path like this: 1, 2, uh, 3, and 4. Okay, so this is the path from 1 to 4. So 1, then 2, then 3, then 4. Okay, so our algorithm is returning only this path. Now we have to check what is the cost of this path. This information is not given. So yeah, this information is given in our adjacency list. So now we have to check our adjacency list, because we are coming from 1 and going to 2. Okay, so 1 to 2. Now in the first step we need to find out the cost of this edge 1 to 2. So to find out the cost of this edge, we have to check our data structure, and in this data structure we will check in at any place if the key is 1. Okay, so key is now 1, and what are the adjacent? So what is the distance value for adjacent 2? Okay, so
Got it.
like this. Okay, so we are reading all the value, and we are checking where is the 2 in our adjacency list, and what is the distance given for this. So we are reading the distance for 1 to 2. Okay,
We will
now
read B only if
yes,
that is 2 we got.
yes. Okay, now in the next step we will check for 2 to 3. What is the distance for 2 to 3 in our data structure? Okay, so we will check for the key 2. Now we will check where the 3 and D is coming. Okay, in our values, and we are reading the distance value D2, like. Okay, now next is 3 to 4. So like we are getting D3. Now then we are adding all the distance D1 plus D2 plus D3 as a cost of this path. Okay, total cost C1. So according using this loop, we are finding this distance for each pair. Okay, so 1, 2, then 2, 3, then 3, 4, 3 to 4. Okay, so this is performing using this graph. So you can do this in another way if you are finding an easy way. So some actually variable value is not easy to understand in this code. Otherwise the same working is happening. Okay, so you can see path I. Okay, so I actually we are reading the value from, you can see what is the length of the path. Okay, so I value is coming reading the index. Okay, so 0, 1, 2, 3, and this g I value is representing first value in the pair, and I in the next line you can see I plus 1. We are reading the second value second in the pair. Okay, and we are checking the what is the distance value. This is coming in the J1. Okay, J0 value is representing the destination, and J1 value is representing the distance from source to destination. Okay, so we are adding this value in our cost S. Okay, and previous cost we are taking infinite, and every time when we are finding out this cost using this for loop, so we are comparing this. If our cost is less than equal to our S value is less than equal to cost, so we are assigning this cost equal to S. Okay, so that means we are comparing the cost for each path, and after finding out the minimum cost, we will return as a answer. And we are also updating our route. So which route contains the minimum cost? So we are at the time of comparison, we are updating this information cost equal to S if we are finding the minimum compared to the previous one, and also updating our route equal to path. And after completion of this uh, process, we will return. Suppose if root is not equal to empty, then we will return the answer. Otherwise, return the not found if our root is empty. Okay, so this is a simple process. You need to figure out that how you can read the data from data structures, and you can find out the cost for the edges. And here there's no algorithm we are using. We are simply reading the data from the data structure and simply comparing the distance, total distance. So this type of problem can be asked in the OPP exam where the algorithm is given. Okay, some extra uh, tasks you need to perform. Okay.
Got it, sir. So this week and previous week was a little bit heavy, sir. Next week will also be heavy, sixth week.
Yeah, you can expect this. Now the from week 4 onwards, every week is actually little bit heavy compared to the week 2 and week 3.
Not compared to week 2, week 3, from compared to week 4 and week 5, sir.
Yeah, so week 4 and week 5. Yeah, week 6 is also heavy, little bit heavy.
Okay.
Okay.
And week 6, 7, 8, 9, this will get heavier, right?
No, week 6 is a little bit heavy, and then week 7 maybe you will find little bit easy. Okay, then week 8 maybe little bit heavy. So not increasing in the every week. Some week maybe you will find easy.
So
But
with the
week 6
course
is
material, with the course material background and preparation, we find it is extremely challenging to face these problems. So if we really want us to really gain, I think there is a step up problem, step up solution has to be really brought it in. There is an interim solution in between it needed. Because it's really complicated.
yeah. So this course is actually a little bit heavy compared to the other course.
No, no, we don't mind in facing the
Mm.
heavy thing, but we are not getting prepared for it, no. So we should give an opportunity to get it prepared. That's where really we welcome the challenges, but
Mhm.
don't have the preparation materials for really facing the challenges.
So
And
material, I think you have enough material. So this content and
no, the
so.
course material is not taking us to the point where we need to reach. No,
Mhm.
this direct discussion and the programming sessions are need to be increased.
Oh, yeah. Actually, in PDSA we are also conducting 3 session. We included this PPA session also.
Sir, I guess
In
like we
fact,
had
in
four
fact,
hour
it's
sessions.
taking.
Actually, sir, one trick I got in PDSC, sir, and wherever I implemented in week 4 and 5, I got the results. And that is for every lecture, if we didn't practice at least 4 times, if I
Yeah.
didn't write the code at least 4 times, then I didn't get that code and the questions from that code. After
Oh,
writing 4 times from every lecture, I'm getting that point only.
okay,
So means
And
you are
every time you need to dry run, every time.
okay,
means you are
okay.
nearly taking around from 20 to 25 hours a week.
What you said?
You are spending nearly 20 to 25 hours a week.
I'm not counting hours, but wherever I means at least 4 times if I do, then only I get. Means for week 4 I did, and every concept of week 4 I got, and
You're
some part of also week 5 I got.
from programming, you're from programming background or non-programming background?
Programming, no programming background.
Okay. So
Means
PDSC.
from mathematics I have done 12th only.
Okay, okay. Yeah, then probably you might be a right measure for general public. Yeah, 3 to 4 times you got to prepare. So this one is really now. This one is really.
And do not write just the code. Do every time dry run. In your mind,